morning, Group A students. Today we're going to go ahead and start the second part of Chapter 1, Part 2, and it's going to continue talking about functions, but now we're going to actually get into more graphing concepts. So today we're going to introduce parent functions. This is Chapter 1, Section 1.6a. The notes, you should have received a copy in class on Tuesday. It was a packet stapled together along with your homework assignment. So the notes you can take with me as we go through the lesson together. So first, we're going to go through 6 parent functions, and these are 6 functions you're going to want to memorize. Make sure that you know the name, the graph, and the domain and range of each function. Okay, so be able to match the graph with the equation as well as the name of the function. First one's a linear function. The easiest way to graph something is just make a table of x and y values. So y equals x is my equation, and then I'm going to get out some y values. So to graph, I'm just going to pick some ordered pairs that are on my coordinate plane. -2, -1, 0, 1, 2. Doesn't matter which ones you pick, I'm picking small numbers just because they'll be on our plane somewhere. Then I plug it in. -2, y equals -2, so -2 is the y. Plug in my x value, -1. Y equaled -1. Plug in my other x value of 0, y equals 0. Plug in x of 1, so y is 1. And plug in the last x value of 2 to get y is 2. And that's our table. Now I'm going to go ahead and plot those points on my coordinate plane. -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and so on. You could just keep going on forever and ever, but I'm just going to do those few points. And you can see our equation makes a line. So this is a line. That's why it's called a linear function. Some other things we need to know about our graph: domain and range. Remember, domain from the last part of Chapter 1 was how far left, how far right. Well, my graph, since it has an arrow on both ends, it goes from -infinity to +infinity for the domain as well as the range. So that's domain and range for a linear function. Next one, it's y equals x squared. This is a quadratic function. Again, I'm going to just write my x values, plug them in, and get my y's. X values, I'm going to choose the same ones that I did last time, -2, -1, 0, 1, 2, and plug them into my equation. Y equals -2 squared. -2 squared is +4. Y equals, in place of my x, I'm going to put the x value -1 squared, which is +1. Y equals 0 squared is 0. Y equals 1 squared is 1. And y equals 2 squared is 4 again. So there's my table of x and y's. Now I'm going to go plot it. -2, 4 is up here. -1, +1, 0, 0, 1, 1, and 2, 4. And then connect your dots together to make your shape, which is a quadratic function. That's called a parabola, that shape. And it makes a U. Now let's talk about domain and range. Domain goes from left to right. My graph, because it's got arrows, it goes forever to the left and forever to the right. The range, how far low it goes, starts here at 0 with a bracket because it has an actual ordered pair at 0. And then it goes on up to +infinity. So that's going to be our domain and range for a quadratic function. Next one is a cubic function. Y equals x cubed. Again, I'm going to just use my equation and plug in some x and y values. I'm going to do the same ones that I've been doing all along, just because they're small. You don't have to, but you can pick whatever ones you want to. And plug them in. -2 cubed goes in for the x. -2 cubed is -8. Y equals -1 goes in for the x. -1 cubed is -1. Y equals 0 cubed is 0. Y equals 1 cubed is 1. And y equals 2 cubed is 8. So I'm just taking my x values, plugging them in, and getting the y's. Now let's go graph it. -2 to -8, -1 to -1, 0, 0, 1, 1, and 2 all the way up to 8. Then I connect my dots together. This one makes kind of a different shape. This makes more of like a snake is what I like to think about it as. But that's a cubic function. The domain, it keeps going on to the left and on to the right. So it's negative to infinity to positive infinity because of the arrows. The range is actually the same thing. Negative infinity to positive infinity because it keeps going on down and then it comes back up. And that is a cubic function. Next one is a square root function. Y equals the square root of x is our equation. So I'm going to pick some x values, plug them in, and graph them. X, I'm actually this time, let's think about if I did pick -2 and -1, 0, 1, and 2. Let's think about what that would look like. Plugging in my x value of -2. I cannot take the square root, though, of a negative. So this does not have any values. I'm going to put a 0 with a line through it just to show that it doesn't exist. Y equals, again, I'm going to plug in my x value of -1. But again, I can't take the square root of a negative number. So this one doesn't exist either. Y equals, the square root of 0 is 0, so that actually had a value. Y equals the square root of 1 is 1. You could choose 2. Y equals the square root of 2. It's going to give you a decimal, so I'm just going to leave it root 2. And since we're talking about square roots, let's go a little bit further. What's another perfect square we could plug in for an x value? 4, right. So I'm going to try 4. Y equals the square root of 4 is 2. Okay, we got some points. Let's go plug it in. -2 and -1, our graph didn't exist there because we can't take the square root of a negative. 0, 0 had a point. 1, 1 did as well. 2 was at root 2, which is like right there. And then 4 was at 2. And then you can connect your dots together. And there's a square root function. Domain of a square root function, how far left to how far right. The leftmost point is 0, and it goes off to the right. The range, how far low, it starts at 0, and it keeps going up to positive infinity. Right? So that's our domain, and that's our range of a square root function. Absolute value is our next one. Absolute value makes its own shape. Absolute value of x, and we're going to get some y values out. -2, -1, 0, 1, 2. Again, you don't have to pick those points, you can choose. Y equals absolute value of -2, because that's my x, is +2. Remember, absolute value makes things positive. Y equals the absolute value of -1 is 1. Y equals the absolute value of 0 is still 0. Y equals absolute value of 1 is 1. And y equals absolute value of 2 is +2. Now I've got my list. Let's go plot them. -2, 2. -1, 1. 0, 0. 1, 1. 2, 2. Then connect my dots together. On this one, you'll notice it makes a V shape for absolute value. That's a way you can remember what the shape of this graph looks like. Absolute values have a V in the name, so they make a V shape. Domain goes forever to the left, forever to the right, so it's positive to negative infinity. Then my range, the lowest it goes is right here at 0 at that ordered pair. So we use a bracket. The highest it goes is positive infinity. That is an absolute value function. Let's do one more, which is the cube root function. Y equals the cube root of x. This is called a cube root because we're taking a 3 cube and we're rooting it. So on my ordered pairs, though, I'm going to be a little bit more selective on what ordered pairs I pick because not every number is a perfect cube. So think about some perfect cubes. -8, -1, 0, 1, and 8. Those are all perfect cubes. So now I'm going to plug it into my equation. The cube root of negative 8, you could type that in your calculator if you need to, but it's negative 2. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of positive 1 is positive 1. And the cube root of positive 8 is positive 2. Again, you can type those in the calculator. Just use the cube root button, or you could just raise it to the 1/3 power. Either way works. Let's go ahead and graph it. Negative 8 is down at negative 2. Negative 1 is negative 1, 0, 0, 1, 1, and 8, 2. Now I'm going to connect my dots together to make my curve. This one makes more of a sideways S shape, or you could think about it as a snake as well. Domain and range. Domain, because it's got arrows, it goes forever to the left, forever to the right. And if I plotted some more points, you would see that this curves down and it curves back up eventually. Takes a little bit of time, but it does curve eventually. So our domain and range are both negative to positive infinity. Those are the 6 most common parent functions that we're going to talk about in the second part of chapter 1. Again, you'll need to memorize the shape, the equation, as well as the name. So I could give you any of those on a quiz and ask you to match them. On the back side of our notes, now we're going to talk about some changes that I can make to those parent functions and how it affects what the graph actually looks like. So one change I can make is shifting the graph vertically. If f of x is the parent function, so if I give you some equation and it's the function, then f of x plus d, if I add something to the outside, it shifts the graph up d units, so whatever d might stand for, shifts it up d units. And if there's a minus on the outside, it does the opposite. It shifts the graph down d units. So that rule allows us to identify what a graph is going to look like just based on the equation. Okay, let's try some examples. Shifting graphs up and down. Graph the function, state the domain and the range. Y equals x plus 5. That's what our equation is. Again, I'm going to do it the same way I did the other ones. Just make a table and plug things on in. Y. Negative 2, negative 1, 0, 1, and 2. Plug it in. Negative 2 plus 5 is 3. Negative 1 plus 5 is 4. 0 plus 5 is 0. 1 plus 5 is 6. And 2 plus 5 is 7. Oops, that's a 5. 7. Now we can graph it. Negative 2, 3. Negative 1, 4. 0 is at 5. 0 is at 5. 1 is at 6. And 2 is at 7. Be careful when you graph these. As you can see, in my table, I made a couple of mistakes, but it's an easy fix. And then you're just going to connect your dots together to make a straight line. Okay? And that's y equals x plus 5. State the domain and the range. The domain, because it goes forever to the left, forever to the right. It goes from negative infinity to positive infinity for the domain, as well as the range. We can tell that from our graph. But the main thing I wanted us to think about was, how does this graph compare to y equals x? Remember, that's the linear parent function. If you look at the front side of your notes, this equation is very similar to y equals x. How does it compare though? Well, as we just talked about, if I add 5 to the outside of a graph, it shifts it up 5 units. So that's what we would say, that's how it compares. It takes the linear equation and shifts it up 5 units because of that plus 5 on the outside. Okay, let's try another example. Graph the function y equals x squared minus 2. Again, I'm going to just pick some x and y values to plug into my function, and then be able to get my table out. Y equals x squared minus 2. Then I'm going to get some y values out. Okay, so first, my x values. I'm going to plug in negative 2, negative 1, 0, 1, 2, just like we did before. You don't have to. You can pick what you want. But now I'm going to plug them in, place in my x. Negative 2 squared minus 2. Negative 2 squared is 4, minus 2 is 2. Y equals negative 1 squared minus 2 is negative 1. Y equals 0 squared minus 2 is negative 2. Y equals 1 squared minus 2 is negative 1. And y equals 2 squared minus 2 is 2. So there's my table. Let's go plot them. Negative 2, 2. Negative 1, negative 1. 0, negative 2. 1, negative 1. And 2, positive 2. And that is what my graph looks like. Okay, how does this graph compare to y equals x squared? Well, let's think about it a minute. This parent function matches which one on the front side of your notes today? Right, the quadratic. So it's very similar to the quadratic function, but the minus 2 tells me to shift down 2 units. Okay, that's what it literally did. It took the whole graph, every ordered pair of the parent function, and just moved it down 2 units. Let's talk about domain and range. Domain, it goes forever to the left, forever to the right, so it's infinities. The range, though, normally our parent function started at 0, but now that it's shifted down 2, it's going to start at negative 2 and go on up to positive infinity. So that's our domain and our range for that quadratic function. Besides shifting graphs vertically, we can also shift them horizontally. So if I give you a parent function and I put something on the inside with the x value, so whether that be parentheses, absolute value bars, whatever's next to the x that's on the inside of the function, that tells me to shift left or right. If it's a plus that's inside the bars or the parentheses, you would think, oh, it shifts to the right because it is a positive. But it is actually the opposite. And that can be tricky to remember. Always shift in the opposite direction. So instead of shifting to the right, I'm going to shift to the left C units, however many units it tells me to. Okay? Then same thing if we go the opposite direction, minus C. You would think, oh, it goes to the left because it's negative. But it actually goes to the right C units because it always goes the opposite direction horizontally. Let's try a couple of examples. Okay, let's try an example with the horizontal shifts. The graph, y equals the absolute value of x minus 1. Again, I'm going to create a quick table just so we can get our points. Y. Now I'm going to plug in some x values all the way down to 2. And plug them in. Y equals the absolute value of negative 2 minus 1 is negative 3. The absolute value is positive 3. Y equals negative 1 minus 1 is negative 2. The absolute value of that is positive 2. Y equals 0 minus 1. Absolute value is positive 1. Y equals 1 minus 1 is 0. And y equals 2 minus 1. The absolute value is 1. Now I've got my table. Let's go plot it. Negative 2, 3. Negative 1, 2. 0, 1. 1, 0. And 2, 1. Because we know, though, let's think about this parent function. What shape does the parent function look like? Right, it's an absolute value function because of these bars, so I know it has to be a V shape. I'm going to connect the dots together, and there's the V. Okay, how does this graph compare, though, to the parent function? Well, it looks the same, except for the minus 1. The minus 1 tells us to take every point, and we're going to shift 1 unit to the right. Okay, that's what the minus 1 does. Shift everything 1 unit to the right. The domain, it opens forever to the left, forever to the right. So there's our domain, negative to positive infinity. Range is it goes from 0, right here. Remember that has a y value of 0, but it opens up to positive infinity. And that's our domain and range. Let's try another one. Graph the function y equals the square root of x plus 2. Again, I'm going to choose some x values and plug them on in. Here's the y. My x, -2, -1, 0, 1, 2, and plug them in. The square root of -2 plus 2 is 0, which is still 0. -1 plus 2 is +1, which square root of that is 1. Square root of 0 plus 2 is root 2. Y equals the square root of 1 plus 2 is root 3. And y equals the square root of 2 plus 2 is 4, which is 2. Let's go graph. -2, 0. -1, +1. 0, root 2 is like right up here. 1, root 3 is a little bit closer, and 2, 2 is right there. And there's our function. Y equals the square root of x plus 2. How does this compare, though, to the parent function, the square root function? Right, the plus 2, what does that tell me to do? It tells me to go how many units? Well, 2 units to the left. Then the domain and the range. Domain starts right there at -2, goes off to the right. The range, it starts at 0 and goes off to +infinity because it goes on up. While I made tables for every function, you don't always have to make a table. If you know what the parent function looks like, and you're able to state whether it went left, right, up, or down, you can draw a sketch real easily of all these parent functions. So like if we review real quick, the first one, how I went up 5, I knew it was linear, so it made a line, and I knew it went up 5 units. Okay, it starts at the origin and went up 5 units. That's a great thing to know about these functions also. They all started at 0, 0, the origin, and then you just moved the shift, up, down, left, right, however many it may have been. So as you look at the next one, -2. Normally, it's a parent function that's a U shape, but it went down 2 units. Normally starts at 0, but it went down 2 units. Okay, let's try going left and right. Same kind of thing, starts at 0, 0. It's an absolute value function, so it's going to make a V shape. The -1 tells me I go to the right. And last one we did was the square root function, x plus 2. I know it's a square root, so I know what that graph looks like. Plus 2 tells me to go 2 units to the left. So you don't always have to make a table. If you're making just a rough sketch like you were on your homework today, then you don't have to make a table. To review what we've done today, if I ask you to sketch a graph and all I give you is the equation, without using a graphing calculator, we need to know the parent function. Well, it's cubic because of the cube, so we know that looks like this. And the -5 tells me to go down 5 units. So how I'm going to sketch it? I know it starts at 0, 0, but I'm going to go down 5 units. 1, 2, 3, 4, 5. And that's what my graph looks like. Again, I did that without a graphing calculator because I know what the parent function looks like, and I know what the -5 does to the graph. I can state domain and range from here as well because it's got arrows. I know that goes from -infinity to +infinity. Next one, state the graph, sketch the graph, y equals x plus 4 squared. Again, the parent function is a quadratic because of the 2. So we know that looks like this from our parent functions. The +4 tells me to take my graph and go 4 units to the left. That's exactly what I'm going to do. Starts at 0, 0. I'm going to move it 4 units to the left and put my graph there. That's what my graph looks like. Again, this is a rough sketch. Domain, though, I can see it goes from -infinity to +infinity because of its parent function. The range, how far low? It goes right there at 0, and it increases to